In this screencast, I'm going to discuss the alternative curvature formula. This is the name I've given to this formula. It's not a universal name. The main message is that if you're doing calculations and if the normal vector is not explicitly needed, then this formula here is much easier than the curvature in terms of the definition. And what is so difficult about this is that computing this quantity, the derivative of the tangent vector, that is painful. And this formula avoids the direct calculation of this. Now you'd have to compute this if you need the normal vector. So if you're going to do that anyway, you might as well compute the curvature this way. But if you don't need this vector, you certainly want to, in almost any case, compute the curvature using this formula. All right, and I have here a quick little example. Given this parameterization, compute the curvature at t equals 0. All right, so what could be a simpler parameterization in 3D? T squared, t cubed. So t equals 0 here, let me just say that corresponds to the point 0, 0, 0. Let's do this quickly. We need r prime. We then need to differentiate again. And now we're pretty much finished differentiating. We just need to evaluate these at the point in question. So we need r prime of 0. We need r double prime of 0. We're also going to need the modulus of r prime at 0, but that's just 1. And with these three quantities, we can now get the curvature. I'll do one intermediate step. We're going to need to take the cross product between r prime at 0, r double prime at 0. That is to say, the cross product of these two vectors. Now, this is actually a very easy cross product to do, but I'm going to, for practice, I'm going to write it out formally. I, j, k, and we take the cross product, 0i, 0j, plus 2k. All right, so hopefully you can do that. We can then go to the curvature formula. That'll be the magnitude of the cross product over the magnitude of the derivative cubed, which is simply 2, and that is the correct answer. I'll challenge you to go and compute the curvature by taking this formula, and you'll see just how much more complicated it is. One final thing is I've written a little demonstration of how you derive the formula here. I'm going to let you pause the screencast if you want to go through the details. I would just point the direction it goes. That's the tangent vector, and what I'm going to do is do some manipulations. Well, basically, I'm going to do manipulations in this order, and using the first and second derivative of the parameterization, I'm going to get a relationship between this magnitude of this cross product and the magnitude of the derivative of the tangent vector. I can just then evaluate what the curvature is from the definition and show that it reduces to this. I will leave it to you to go through these various steps in the order indicated here, down, and over if you wish.